Information Sciences Division. He's been at the lab since 1983. He has a very distinguished career in human language technology and in speech signal processing. He's served at the laboratory in many different capacities, as well as on government assignments, as well as he's serving on the Massachusetts State Task Force on Artificial Intelligence. He holds both a bachelor's, master's, and PhD degrees in electrical engineering from MIT. And he has a really fascinating talk up ahead, and hopefully we're going to inspire you guys to do some great things with your project. So with that, all right, thank you everyone, and over to you, Marc.
Thanks, Jen. Can you see the slides okay? Good morning. My name is Marc Zissman. I work at MIT Lincoln Laboratory, and for the last 3 months, I've been part of what's called PACT, a project to do private automated contact tracing. The purpose of my talk this morning is to give you a sense of the mission of PACT and give a status update, especially for the Beaver Work Summer Institute students. PACT itself is a collaboration that includes researchers from around the world. It's led by folks from the MIT Computer Science and Artificial Intelligence Laboratory, CSAIL, by Massachusetts General Hospital, the Center for Global Health, and also MIT Lincoln Laboratory. And the sponsorship is from DARPA and IBM Research, and then also we're in affiliation with NIST. So before I start telling you about PACT, I'd like to tell you a little bit about myself. So I grew up in Chicago, in a suburb of Chicago called Lincolnwood in the 1960s. My mother is a teacher, was a retired teacher. My father was an attorney, and there were no engineers or scientists in my family. So I was kind of the first one to make a career out of doing scientific and technical research. I worked when I was in high school, I worked for 4 years. My first significant real job was at a neighborhood deli where I made corned beef sandwiches, hundreds, maybe thousands that looked just like that. I graduated from a large public high school called Niles West High School in 1981. And I'd like to point out that one of your BWSI colleagues, Henry Gussis, will graduate from that same high school next year, so 40 years later. After high school, I went to MIT, and I was at MIT as a student for almost 10 years on and off, where I was an undergraduate and a graduate. I got married while I was there, shortly thereafter, kind of during that time, to my wife, Tori. We have 2 sons. And I started working almost immediately at Lincoln Laboratory, which is a part of MIT. So I started at Lincoln Laboratory in the summer after my sophomore year in college when I was 19. And I've worked at Lincoln Laboratory for the last 37 years as an intern, technical staff, and then in management. In that time, the technical work that I've done has primarily been in the areas of human language technology, which is how to, for example, how to extract information from speech, like who's speaking, what they're speaking about, and so on, the kinds of things that Siri and other applications do very well today. But back in those days, there was no Siri. And so we had to program that ourselves on special purpose hardware. Then I moved into doing what's called wideband tactical networking, which is basically how to make sure that soldiers, for example, on a battlefield can communicate with each other, even in the absence of communication infrastructure. And then finally, I moved into the area of cybersecurity. And during that time, I did a number of other interesting things at least that I found interesting. I spent a year at the National Security Agency. I worked in Haiti after the terrible 2010 earthquake for several months. And I have served for the last 8 years on something called the Army Science Board, which is a group of people that advise the senior leadership of the Army on things that are technical and scientific. And so that's kind of who I am. You won't see anything in there about contact tracing or diseases and so on. That's not my background. My background is very much engineering. And even though I'm going to talk to you today about something called contact tracing, that was a term, that was a phrase that I had never heard up until kind of the end of March of this year. So I'm by no means an expert. I'm not an expert in this area. And the good news is that next week, you will hear from Dr. Louise Ivers, who's an infectious disease specialist, doctor, someone who treats COVID patients and who has worked for decades in trying to track down how it is that infectious diseases start and spread, and then how do you mitigate that spread? How do you get rid of a disease within a population? And so, if you have questions about that or are interested in that, That's something that Dr. Ivers will be able to answer all of your questions next week when she briefs you. So enough about me. Let me talk a little bit about the limited amount that I understand about COVID-19 infection progression. And so this is, again, something that Dr. Ivers can speak to. But as I understand it, there are people who get exposed and who become sick. And in the medical community, public health community, those people are called index cases. And so these are people who are sick. Maybe they were exposed at one point. The disease incubated within them some number of days, and then they became infectious. That's what this dark blue or purple shows. And they're infectious for some number of days. And then eventually they recover and they're no longer infectious. The problem with COVID, and maybe other diseases too, is that there's this time between when they become infectious and when their symptoms begin to show. And so it means that you can be infectious with COVID and you can be coughing up COVID virus and infecting other people. Even if coughing may be a bad example, you can be breathing out COVID virus, even if you're not showing any symptoms, even if you don't feel sick, even if you're not coughing, even if you're not sneezing, and so on. And so that's confusing and dangerous because, if you're not showing symptoms, there'd be no reason for you to think you're sick. So you're not limiting what you're doing, and you can be infecting other people. And that's exactly what's shown here. So here we see a contact. So this is a person who's not yet sick, but regrettably, for whatever reason, they come into contact with somebody who is infectious. And when that happens, this whole cycle starts all over again. And they maybe have a period of incubation, and then they become infectious, and so on. And so the goal of contact tracing really is to find this infected contact before they can infect others. So as soon as possible after this person starts showing symptoms and you test him and you find out, yep, he's got the virus, you wanna then backtrack and figure out all the people that this index case came into contact with, including this infected contact, and you want to get this person basically out of circulation, or you at least want to test him and possibly get him out of circulation before he can infect other people, right? That's the goal of contact tracing, again, as I understand it. So this is another way of thinking about it. This contact tracing is an epidemiological technique that's used to identify people who have had contact with an infected person. And so you can see this is maybe like the index case, and they transmit it to somebody else and somebody else and somebody else. And what you're trying to do is limit this. You'd like, as many of these reds, these infected people, to be actually uninfected is what you want. You wish that they could all be black in this picture. Now, contact tracing has been used for a long time. So people in public health, doctors, others understand this very well. But the problem is that in places like Massachusetts, where we do contact tracing, for the most part, it's for diseases like tuberculosis or smallpox. Of course, we don't have smallpox in the United States anymore, or sexually transmitted diseases. And for something like tuberculosis, last year in Massachusetts, we had about 200 cases. So that's like one case a day, something like that. And that's very manageable because, you can do with paper and pencil and phone calls. You make phone calls, every case that comes in, there's one a day. You can track down who that person was near, and you can try to stamp it out. And the other good thing about tuberculosis, if you want to say it's good, is that it takes about 10 years to kill you. So you have time to find those people, to test them, and to get them out of circulation until they're cured. And that's tuberculosis. With COVID, Massachusetts had thousands of cases of COVID per day just a month ago, and COVID can kill you in a week or two. And so, how to apply contact tracing to something like COVID is really tricky compared to tuberculosis, okay? But there are other challenges. So let me just describe what those are. So up until COVID, contact tracing was really a manual process primarily. And you had telephone, you could call. If somebody says they're sick or they go to the hospital to get tested, they're sick. A contact tracer, usually in their local town or city, at least within Massachusetts, would call them and ask them who they're near, who are their family members, and maybe suggested those people go in for testing. And you could use Excel spreadsheets, or you could even write this down on a spiral notebook, you'd be fine. But, the index case has to remember who they were in contact with and where they were. And this is labor intensive. Even if you have only one case a day, contact tracers have other things to do. And so it's time consuming. And it just doesn't scale to go from one person a day in a state like Massachusetts to thousands of people per day. But another problem is you have to ask the person well, who were you with? Well, if that person was on a train or on a bus or, you know, at a Starbucks or whatever it might be, they may not know the names of all the people they sat with. If yesterday they spent an hour at a Starbucks sitting next to somebody who just happened to be there at the same time, kind of breathing on them and having that person inhale, you know, even though they weren't doing it on purpose, you just don't know who you were near. And so that's a problem that even applies to things like tuberculosis, but that's especially true for things like COVID. And so advanced contact tracing tools are needed, both to address the scale of COVID and also to address the problem that you don't always know who you were close to. So how did PACT get started? So this PACT project got started in late March of 2020. So I forget, it was the middle of March, the last week of March. And what happened was MIT Institute professor Ron Rivest. So an institute professor, MIT might have 10 or 12 or 15 institute professors. These are the most senior, most well-respected professors at MIT. That's the highest kind of professor that there is at MIT. At other universities, you might call it a university professor. You might hear that term. So Ron, who's also, by the way, a Turing Award winner, which means that the Turing Award is sort of like the Nobel Prize for computer science. And Ron's got a long, I don't know, 40, 50-year history in developing doing cryptographic research into cryptology, which is how to make and break codes. And Ron's work it affects all of us every day. So the only reason that we're able to do secure communications on the internet and buy things securely and so on is because of the codes that Ron and the protocols Ron and his colleagues have developed. So Ron and his colleague, Professor Yael Kali, were teaching a class of graduate students. In fact, it was the last class they taught at MIT face-to-face before MIT closed down for COVID. And they were teaching something, this thing called the Find My protocol. And the Find My protocol is the thing that exists on Apple iPhones to help you find your phone if it gets lost. And I don't have time to go into the detail, but it's a really cool protocol, and it's done in a way that preserves privacy, which means that it allows communication between phones in such a way that no personal information about the phone or its phone number or its owner is passed to the other phone, and yet you can still use it to help find your phone. So it's pretty cool. And it uses the Bluetooth low energy protocol for proximity detection. What that means is it uses this protocol to detect when two phones are close to each other without knowing exactly where the GPS location of those phones. So it does this, it's proximity detection, meaning it detects other phones that are nearby without doing geolocation, which means without mapping those phones onto a map of the world kind of thing. So we at Lincoln Laboratory had worked with Professor Rivest and also perhaps with Professor Kale. I'm not 100% sure. We worked with Yael, but definitely with Ron for years. In fact, Ron had visited Lincoln Laboratory not even a month prior to the outbreak of COVID. And so we knew him, but we didn't know he was working on this problem. And it was the president of MIT, President Raphael Reif, who reached out to the director of Lincoln Laboratory and said, hey, you guys at Lincoln ought to try to provide some technical support to what Ron's doing. And so my boss is the director of Lincoln Laboratory, and he reached out to many of us at Lincoln and said, hey, go figure out what Ron's doing and see if you can help. And that's what we did. And so this became what we call a campus-led effort, meaning it was led by CSAIL, the Computer Science and AI Lab, where Ron works and where Yael works, together with the Internet Privacy Research Initiative, which is, I think of as an initiative on campus that's associated with CSAIL. And by the time Lincoln people got involved, which was the end of March, this was already a worldwide collaboration involving Israel and Australia and lots of other countries and lots of other universities, Boston University and Brown and so on. And the focus was very much on private proximity detection. So at this point, people were still talking about using GPS, possibly to try to detect when two people were too close for too long with respect to COVID. But Ron and his colleagues were not interested in using GPS. They wanted to use Bluetooth, and they wanted to do proximity detection. So they wanted to keep it very private. So PACT, which stands for Private Automated Contact Tracing, the P, the lead letter, is really important. It has to be private. For Ron to be interested and to put effort into this, he wanted to make sure it was private, because remember, his whole career has been spent doing cryptography to make sure that information that is private or that is encrypted stays private and stays secure and stays hidden from people who shouldn't have it. So Lincoln Laboratory got involved, and then very soon after that, our colleague Louise Ivers also got involved. So Louise, as I said before, is an infectious disease specialist at Mass General Hospital, which is this very large teaching hospital in Boston. and she's a public health research leader. And people at Lincoln Laboratory and I specifically had worked with Louise before on other things, and she joined the team as a senior medical advisor. And so that, although we had, of course, Ron, who knew cryptography, and Danny Weitzner, another leader who is a leader in terms of privacy, this gave us now a lead who could explain to us all the public health issues of how you do contact tracing. And so that was very helpful. And really, by the end of March, we went from having nobody at Lincoln working on this to having about 100 people working on this, some of them full-time, some of them 18 hours a day. So it grew very quickly. And so what were we, all of us, trying to do? Well, I know you've seen the video before. You can click on this video if you like. But basically, we were trying to use Bluetooth to try to figure out when two people had been too close for too long. So there's this thing called contact detection, maybe we would call it now exposure notification, where this red person, this index case, this sick person, and this contact become too close, meaning maybe 2 meters or less, 6 feet or less for too long, meaning, I don't know, 10 minutes, 15 minutes, could be longer than that. And then what happens is if these people both have phones, they're chirping at each other. They're sending out these codes that have no private information. They're not even encrypted private information. They're just random codes that get sent between phones that based on the Apple Find My protocol. But if an index case then gets sick, or he realizes he's sick and he goes in and he gets a test and come to find, yep, he's got the virus. What would normally happen is, in Massachusetts, at least, other places, is that someone would interview him, and they would ask him all these questions about who he's been near, where he's been for the last 14 days or whatever it might be. And then we would try to, the command center would try to find those people and warn them that they had been too close to a person who was this index case. And then those people would be advised to, keep track of your symptoms, or maybe go get tested yourself, or maybe self-quarantine, which means quarantine means that people who may or may not be sick, we're not sure, but they've been near a sick person, they just stay home. They just stay home and try not to be near anybody else for some period of time. So this is kind of the existing system that we even have today in Massachusetts, and that we have in many other states and countries. What the automatic system does is it says, hey, do you have the same person can ask, do you have a phone that's been enabled for automated contact tracing, that's been keeping track of the chirps it's been sending up and the chirps it's been seeing? And if the answer is yes, then the person is asked, they don't have to do it, but they're asked, would you mind sending up the chirps or the seeds, the crypto seeds associated with those chirps? Would you be willing to send those chirps up to a database? And then what we'll do is we will send this database periodically to everybody else who has a phone and who has this app installed. And these people will then, we'll then compare all the chirps that have been sent by sick people to all the chirps they've actually seen in the past 14 days. And if there's a match there, then regrettably, they've been too close for too long to someone who's sick. Now, they don't know which person they've been too close for. They don't know where that happened. We might tell them the day it happened, but they will be told, hey, just like these people were told by Matt, because this guy remembered who he was close to for the past 14 days, and this person interviewed him, these people will be told that, it wasn't through a manual interview. It was really through the app that we noticed. Maybe it could have been on the train, could have been at a coffee shop, whatever it might be, but you were too close for too long. And so you need to go do all these same things, maybe keep track of your symptoms, or maybe go get tested yourself, or maybe self-quarantine. So this automatic system is it's a supplement. It doesn't replace this manual process, but it's a supplement to the manual process. And so the hope is that it contacts, some of these people could be the same as these people, right? If I'm at home and my wife is one of the people who's been sick, my wife will remember that she's been near me for sure. But also our phones have been close together. And so there could be an overlap between these two sets. But hopefully, or not hopefully, but maybe, likely, there are some people in this set that would not be in this set. And so that's where the automatic tracing comes in and where it provides value. So as I said, you can go to this video and go watch that and probably get another description that's even better than what I just gave you, but it basically describes the same thing. Now, if you've been reading the paper or whatever, going online, listening, watching television, you would know that there is this smartphone-based disease tracking is being used in many different countries. And I don't have time to describe how this works exactly in each of these countries. There's different approaches, and regrettably, this picture is already out of date. This picture was good about a week ago. It's already changing. But there are different ways of doing it. And some of the countries shown in red, some of them will use GPS, right? Which we would not use in the United States because that would not be constitutional probably. And then the countries in blue and green are doing some form of the Bluetooth tracking that I showed you on the previous chart. And the difference between blue and green has to do with the difference between centralized and decentralized proximity detection, which is all about where the chirp matching gets done. If it gets done in your phone as a potential contact, that's called distributed. So that means everybody's phone is doing this matching. If it gets done in the cloud, if it gets done in that database, and then you just get told, hey, you were too close for too long, then we call that a centralized system. And I'm going to generalize here, but for the most part, most of the systems in most countries are becoming decentralized. That's a more private approach. And that is the approach that Apple and Google support. And that matters because almost all of our phones worldwide are either Apple or Google phones. So what you're likely to see in your state, if you live in the US in the coming months, maybe not everywhere, but in some states, is this. And so that's just the same picture I just showed you, except now you can see that what you will get is, what I showed you before was a notion. It was a model, an architecture. But this is going to be real now. So you will, if you opt in, you will get on your phone an app that will support both the contact detection part of contact tracing and also the exposure query notification part. Now, mostly this part is done in the operating system. And if you have, for example, an Apple phone and you have iOS 13.5 or greater, then it turns out you've already got the software in your phone to do this. But you can't turn it on because as of today, the middle of June, end of June, of 2020, there are no apps available from any state that will let you actually turn on this contact tracing within your phone. So that's what's coming. No state has done it. Apple and Google have made it such that there will only be one app per state. That app will get approved by the state and by Apple and Google and so on. But eventually, maybe in a month or two, this will become available. Maybe sooner than that. North Dakota is moving forward on this. The other states are getting close, but as far as I know, there's no state that has this. There are not even really any countries that have an Apple Google compatible app that's widely deployed. I think Switzerland is very close in the last couple of days. Germany also very close. Maybe they've gone live, but this is new. This is all new in the last week or two. So certainly a month ago there was no country that had this. Maybe this week there are a couple of countries that have this, at least in pilot form. This database of anonymized contacts, this is going to be in the United States. This will be every state will have to pay an IT company to maintain this for them. And of course, these are going to have to be synchronized across state lines because people move around state to state. And you're going to need to make sure that, for example, Lincoln Laboratory has lots of people come down to work from New Hampshire. We want to make sure if somebody gets sick, that even if they have the New Hampshire app, that folks in Massachusetts can be warned that they might have been close to these people. So that'll have to get done, and it'll have to get done across countries too. For Apple and Google could have decided to have one worldwide database of anonymized contacts. They decided not to do that. That was a technical decision they made, a political decision also. And so that means that falls to the states and the countries to do that themselves and to sync these things up. So this is what's coming. And as I say, in some countries, a few countries have this today, and hopefully some states in the US will have it before too long. And what it'll look like is some kind of app on your phone. And this is just a mock-up of what it might look like. And individual citizens will have this. You'll be able to turn, it'll alert the user of potential exposure. It'll tell you what to do. I suppose it'll let you turn it off if you don't want to have it. You have it for a while, you don't want to have it. You can turn it off, turn the exposure notification off. And then there'll be some kind of dashboard. This is a mock-up. I'm not sure it's going to look just like this, but public health professionals will have some way of tracking what's going on in their states while still at the same time maintaining as much privacy as possible. So this is all great. So what's actually the technical challenge here? The technical challenge is this. We don't really care about measuring the exact distance between people, okay? That's not the goal. The goal, from a public health perspective, is usually something like, just tell me who was too close for too long. That's what we call it, TC4TL, too close for too long. And what too close usually means 2 meters or less, 6 feet or less. And too long is usually something like 10 minutes or longer, or maybe it's 15 minutes or a half an hour, whatever it might be. And so you can think about, if you're side by side at the coffee shop, and you're there for an hour, that's too close for too long. Now, there are some things like a hug or a handshake, those would be very close for a short period of time. Now, if while I'm hugging you, I sneeze at you, that's bad news. But we're probably not going to detect that with these phones, right? So somebody is going to have to draw. It could be a box like this, or maybe it's a triangle, or maybe it's a line. We don't really know. That's the public health job. The public health department in your city or town or your state, or maybe the CDC will give advice to the states. That's the public health authority's job. And then our job as engineers is, however they draw this red region, our job is to implement that. And that's what we're all of us in the US and elsewhere trying to do. So it's a subtle difference, but again, we don't really care if you're 2 feet apart, 2.5 feet apart, 3 feet apart. That is a detail. The real question is, were you too close for too long? That's the problem that we as engineers are trying to solve. And to solve that problem, we've developed at PACT, we've developed what we call the PACT Stack. So layer 1 is proximity measurement, and this is done with Bluetooth, in fact, using, as I'll show you in a minute, using energy measurements. Layer 2 is how the chirps move around in a way that's private. Layer 3 is the interfaces, both the app interface on the phone, that's what we call layer 3B, and the interface to the public health system, which is, for example, the system of record that every state has to maintain of who has a disease that's serious. And that's what we call layer 3A. So layer 1 and layer 2 are implemented basically by Apple and Google in the operating system of their phones. And so, we prototyped that within PACT. A lot of that was done at Lincoln Laboratory. Some of it was done on the MIT campus. And so we understand this very well, and we've made recommendations to Apple and Google and what they should implement, and they've basically done that. We weren't the only ones that suggested that, but their implementation at layer 2, especially of moving these chirps around, is very good. It's very private. It's great, right? There's always room for improvement. We may suggest to them other things they should be looking at, but they've done the right thing here. Layer 1, they've done the best they can at the moment, right? There are things they could do to make it better, but this is the problem. And I'll show you in a minute why it's still a technical challenge to estimate distance, range, we call it, from Bluetooth, which was not designed to measure range. Layer 3A and 3B is easy. This is just an engineering challenge. There are plenty of companies that can do this, companies that do medical IT software or that do medical apps on phones. And so this is all easy, can be done. Every state is going to have to pay somebody to do it. Every country is going to have to pay somebody to do it. But there's really no technical challenge here. This is just straightforward engineering that has to be done, has to be designed right, not a big deal. So the big engineering challenge is layer 1. And let me tell you why that's such a challenge. It turns out that we and many others around the world, while everybody was holed up in the end of March, beginning of April, started making energy measurements between our phones using Bluetooth Low Energy. And what you can measure is what's called RSSI, basically the signal strength between the received signal strength between two phones. So when my phone is beaconing at your phone, it's chirping at your phone using the Apple Find My protocol, or now what's become like this COVID protocol that Apple and Google have implemented. You would think that, the way RF, radio frequency energy, works, that the farther out my phone is away from your phone, the weaker the signal will be that I will receive. And to some extent, that's true. You can see that here in this case. So here you see distance on the x-axis from 5 feet out to 20 feet, or 0 feet out to 20 feet. And you see the received signal strength. And we just wish this was just a bright orange line, a very thin line from up here to down here, but it's not. The received signal strength is affected by many things, like, is the phone in my pocket? What's the orientation of the phone? Is the phone next to my head? Is my body between my phone and your phone? Because my body, which is made up of water, is going to absorb a lot of that energy. And so the phones could be the same distance apart, but if I'm in the way of my phone and you're in the way of your phone, especially, the signal strength could be a factor of 100 less than what we call 20 dB less than if the two phones are also the same distance apart, but our bodies are not between them. And so that's unfortunate, but that's just the way it is. And so the question is, how are you going to estimate distance accurately from this received signal strength, which I can show you here, I'm showing you here, is so variable. And so I'm not going to get into all the details, but if you just do it in a very simple way, which is basically what Apple and Google are doing now, you get this kind of a curve. So this first of all, let me introduce you to decision error trade-off curves. So there's two mistakes you can make, right? You can do what's called a false alarm, or what's called a false positive, which means that you can say you were too close for too long, but you really weren't. That's an error. And then the other error you can make is you can miss it. So that means two people were too close for too long, but your system didn't detect it, right? So those are the two errors, and you can trade those off for each other. And in what's currently implemented inside the Apple and Google phones it allows you to operate on this, basically on this red dotted line, which has what's called an equal error rate, the point at which the miss is equal to false alarms, of something like 25%. So that's actually not very good. And then as you get progressively more clever, you can reduce that error rate down to about 7%. And you can do that without impacting the battery, because remember, these phones are not primarily designed to do COVID-based range and time detection. They're really for playing music and doing email and doing texting and all the other apps that you use your phone for. And so we need to make sure that even we can make them good. We'd like to make them good for doing too close for too long detection without ruining the battery, without running the battery down to 0 in 15 minutes. And folks within PACT have shown how that's possible. And they are gradually even moving this. You want to be way down here is where you'd like to be. And we think we have some ideas for getting way down here, but we can at least get to right here without using too much more battery on the phone. And so that's what we're talking to Apple and Google about, is how do you go from this red dotted line down to this green solid line? We've shown them how that can be done. The question is, will they be willing to do it, given the changes it will require to their operating systems and the impact it might have on their battery? So if you're interested in this, we've got a paper on it. You can ask folks, the BWSI folks, or send me an email. We'll be happy to send you the paper that describes exactly how this is done. We have a lot of data available, and you may wish, I'm sure you're going to get data through the BWSI process this summer, but just in case you want more data, you can go to GitHub and get even more data for this project that we and others are uploading. And some of this data is coming not from people using their phones and moving around their homes with phones, but from robots that are doing that. And so I'm going to try, I'm not sure this is going to work, but I'm going to try to show you a YouTube video that shows how that's happening. So let me share. Let me now choose if I can figure it out. Let's see. Let me share that. Oh, I think I shared the wrong one. Try it again. This one. So I'm going to just play a little bit now of this video. And so hopefully what you can see is that these robots have been programmed to move around. And so you could ask yourself, well, why would we use robots for that? And of course, you know the answer is that it's not safe to have humans get that together just to collect data. It's not reasonable to put humans at risk to do that, at least today, at least in Massachusetts. And so because of that, we chose to have robots do it. We do some of this work at Lincoln Laboratory. There are other places like this place called Waypoint Electronics, where we're also doing this work. Others are doing it elsewhere. And all that data that we're going to collect about, these robots had phones in their hands and they're moving around, and we're collecting all the data, the signal strength data between those phones while they're moving around. And we'll make all that data available publicly. And then what we're going to have is a big evaluation. We'll hopefully do this multiple times. NIST is a part of the government, and their job is to do standards and technology. And so they will, but other things they do are like evaluations. And so, people will be able to use machine learning and other approaches to try to figure out who can come up with the best way of calculating too close for too long. And so you might be interested in that either during the summer or afterwards. And so please, again, feel free to take a look at the site. If you have any questions, ask whoever it is you're working with, whoever's guiding you on BWSI, or if they don't know the answer, please come ask me, email me, and we'll try to get you the information you need. Now, we would love to get this out into the states and into other countries as quickly as possible. I've told you that some countries are already doing this. No state is doing it yet, but maybe by the time you watch this video, there will be a state or two doing it. But before we can, if we want to, before we do states, we can do pilots. And so pilots means, we roll it out, but to a small segment of the community for a short period of time. That could be college dorms, hospitals, campuses, whatever businesses, whatever it might be. And we are in the process of doing that right now, actually, with the military, with a university, with MIT, and elsewhere. And we're very excited about that. And we hope to learn a lot from these pilots, and that should inform how we roll it out, how states roll it out as well. We have many accomplishments in the 3 months that we've been working on PACT. We had a conference which was recorded. So if you're interested, it was introduced by our governor in Massachusetts, and then lots of technical talks. You could look at that. It's at the pact.mit.edu website. We are also serving now as a trusted technical advisor to the CDC and to a couple of states. That's exciting. And we work very closely with Apple and Google. We have weekly meetings with them, mostly on what we call layer 1 on the Bluetooth side of things, but also on the upper layers as well. And so that's very exciting because, at the end of the day, how layer 1 and layer 2 get implemented is up to Apple and Google. But if we can give them good advice, good technical advice, and explain why it's important, there's a chance that they will, they want it to work as well as it possibly can. And so there's a chance that they will agree and take our advice and implement some of these things in their phones. And so we're very excited about that. And it's a great working relationship. Apple and Google, of course, in the real world, normally are very competitive. But in this case, they see eye to eye, and they're working with us as one team. There's no daylight, really, that we observe between Apple and Google as far as contact tracing goes, which makes it a pleasure to work with them. There's many advanced concepts we're working on. I'm not going to describe all of these, but one of them I will talk about is ultrasound. So it turns out that using Bluetooth was never designed to do this kind of range measurements that we're doing with it. To do it as accurately as we'd like to do it. But ultrasound, boy, that's which basically you chirp out real chirps. Ultrasound is sound that's usually a frequency slightly above what humans can hear, what most humans can hear. Maybe dogs can hear it. But it turns out from our initial experiments that ultrasound allows for very, very precise measurement of distance, to get distance measurements that are very accurate to within a foot. And that would be great for too close for too long. The problem with ultrasound is just battery usage. It's not built into the operating system. So you need an app to run it, and then the apps take a lot of battery. And there's ways of actually using Bluetooth and ultrasound together that people are experimenting with at the MIT campus and elsewhere, other universities, CMU, and also Lincoln Laboratory. And so we're looking at that. We're also looking at what are called wearables. So some people aren't going to have phones because maybe they're older people or maybe children that don't have smartphones yet. Poor people might be. So it might be possible to use these wearables to give the same capability to folks who can't get it through their smartphones. And of course, those wearables could be compatible with Apple and Google, but they might not have to be compatible. And if they're not compatible, then maybe using ultrasound and so on becomes an option in a way that works from a battery life perspective. So I'd just like to conclude, and hopefully I've convinced you, well, hopefully I've told you, and you'll hear again more from Dr. Ivers next week, that contact tracing combined with public health actions such as testing and quarantining is really the gold standard for reducing the spread of any virus, including COVID. And we hope that automated contact tracing could supplement manual efforts because a lot of times you just don't know who you were close to. But if the two people have phones, they don't need to know each other. Those phones can be exchanging these chirps. And if one person gets sick and then the other person can learn what those chirps were, the chirps from sick people, they can do those matches and find out that they were exposed. PACT, this private automated contact tracing effort, is seeking to advance the state of the art in private automated contact tracing solutions. And there's a lot of technical challenges, how to use Bluetooth, maybe ultrasound, other things that still exist that we're working through. So our job at PACT is really to serve as a trusted technical advisor to different government public health authorities, and to also kind of serve as a center, even a virtual center really, for collecting and sharing data and best practices. So with that, I'll stop and be happy to take any questions you might have.
All right, Marc, thank you very, very much. That was great. I think the slide deck was great, and the students are definitely very, very curious. There are a lot of questions here. I've been keeping up with some of the questions, but one common theme is what the difference is between centralized and decentralized contact tracing. Could you, so I've given them a little bit in the Q&A, but maybe you could expand on that?
Yeah, sure, I can. So, so this is, it's kind of a religious war. as to what's better or what's worse. Um, Let me describe decentralized contact tracing. It all has to do with where the chirps go and where the chirps get processed. So in a decentralized system, if I get sick and I'm asked to upload the chirps that I've broadcast, those will go up into a database. And then, like Jen, if Jen is just a resident of Massachusetts like I am, and she has the app on her phone, then maybe once a day or some number of times each day, she will go to her phone will download all the chirps, the seeds really that go with those chirps. We'll download all those seeds into her phone, and she will compare all of those, call them sick chirps, to all of the chirps that she's heard over the last 14 days. So that comparison happens on Jen's phone. And it's called decentralized because Jen is one of 7 million people in Massachusetts. And if everybody had this app on their phone, then that comparison process would happen in all 7 million people's phones, right? That's why it's called decentralized. The centralized approach says, well, no, that's not what we're going to do. We're going to, yes, when you're sick, you're going to send up the chirps that you sent. That's great. But I also want everybody to send up all the chirps that they heard every day also. And the centralized system, the one, think of it as some computer center in Boston is going to do all that matching. And it will then tell Jen whether or not she's been near somebody. It will know. And it will go back to Jen and say, Jen, sorry, bad news. Yeah, I'm not going to tell you who you were near, but you were near somebody who's sick. And so so you would say, well, what's the difference between those two things? I mean, why does it matter? And I guess Professor Revest would say, and others would say, that the distributed approach is it's more private, because the only time I share anything is if I'm sick and if I choose to, I share the chirps that I've sent out, and that's it. The person who the contact doesn't have to share anything, right? So that makes it very private. If something goes wrong, if somebody breaks into the database, all they can see, I mean, it shouldn't matter. All those chirps just are random bits of data, and they're not connected to anybody. So that seemed more private to Professor Revest and to all of his colleagues, and I guess I kind of agree. The countries that do centralized, like the UK is about to change, but the UK is one, Singapore is another, Australia was another. There were two big problems. So one was a political problem, and one is a technical, one is the real problem. The political problem is that really they can know who is sending those trips. It's just not as private. They can figure out who the sick people are, and they like that idea. They want to know that. They say, look, we're a public health department. We ought to know who's sick. That's just the way it is. We're not going to track people's GPS, but we want to know who these people are who are sick. And so those countries made that argument, and they said, and by the way, we're not interested in what Apple and Google tell us we can do. We will do what we want to do. Apple and Google said, no, you won't. We will not let you use our system that way. And so they don't. And so any country that runs a centralized system, it just doesn't work. It doesn't work as effectively. So especially on the iPhones, it is really hard to run a centralized system when you're fighting the operating system as opposed to working with it. And that's why the UK is going to switch over. Singapore, they may get away with it, and they may choose not to do that. But in the long run, almost every country is going to go with a decentralized system, because that's the only system that Apple and Google will permit. Because for Apple and Google, this is a nightmare. They don't want to be doing contact tracing. They want to be selling music and selling phones and selling cool apps, and yet they've been forced into this. And they don't want to do anything that would compromise the privacy of their customers. Like Google compromises the privacy of its customers all the time. It's just that Apple doesn't. It's just that Google does not want to do that for contact tracing. For contact tracing, they want to be squeaky clean, and they are. And Apple is squeaky clean. And these countries that want to compromise, Apple and Google just won't have it. And so that's the way it is. Does that make sense?
Yeah, that's great. Thanks. That was very, very clear explanation. Another question that came in is, where will the database of anonymized contacts be stored, and what methods will be used to make sure that the transfer from the infection certification to the database is secure and maintains anonymity?
Right. So good question. So it could have been that Apple and Google could have raised their hands and said, we're going to maintain the database. There'll be one worldwide database. That would have actually, I think, been a good idea. It didn't happen that way. So every state has to pay somebody, an IT company, to maintain that database for them. And so that's hard, but that costs some money, but fine, whatever. And then those databases are going to have to be synced up, because like in Lincoln Laboratory, we have people come down from New Hampshire every day. And so if somebody gets sick and they find that out in New Hampshire, somehow the Massachusetts database has to be updated, and how's that going to work? So that has to all be worked out. And then it's a good question. How do we? You have to certify that the chirps, the seeds that go up, have to be certified, because otherwise bad guys could false alarm the system, and they could say they're sick when they're not, and they could cause havoc. So we've thought about, for example, QR codes that would be one-time QR codes that the Department of Public Health would provide to each testing organization. And so when they say, Mark, you're sick, press this button on your phone, but before you do it, scan this QR code, and we'll send that QR code up with your chirps. And then the database would know that it was legitimate, that I was authorized. If I send my chirps up without a QR code that was good, you'll just ignore them. And so I think that's something like that is what's going to happen.
Great. So there are some questions here on specific to the project, and maybe I can take a crack at answering some of these. So how does piPACT fit into all this? And Marc, we'd like to get your take on this as well. I'll give you my 2 cents. And should we test the pies under portable conditions? So for that, I would say yes, test them under any conditions. See what you can do and see where your approaches break down. Where does piPACT fit into all of this? This is an incredibly hard project. So I'll tell you, privately, not privately, there was a picture in Marc's brief of a dining room in a home. That was my daughter, and that was me trying to get our arms around how hard this problem is. And this is something that, we just want to see what you can do. There's no right or wrong answer. We've been hammering away at this for a couple months, but I know there's a lot of innovative, creative ideas that you guys can come up with. So I'm just really curious and excited to see what kind of out-of-the-box things you can come up with. Earlier in the Q&A, there was a question of, well, could you enter, is it in your pocket or is the phone in your shirt? And that is critical. That's one of the things we found was really a critical separation in the distributions of the signals. So whatever you guys come up with, we're watching, and if you have some great ideas, we'll bring them to the PACT team for sure.
Yeah,
Marc,
I would just add on, Jen, to what you said. So with our colleague Bob Shin, who's the director, the founder of BeaverWorks, we've always been, I'm sure you have been too, Jen, always been impressed with what both the BWSI, the high school level, and the main BeaverWorks part, the undergraduate level, students have come up with. And I, without going into all the details, it's definitely true that BeaverWorks, that the ideas that have come out of BeaverWorks, whether at the high school level or at the college level, have already had impact on both national security on the one hand, and also just on the commercial marketplace. And that, a lot of stuff has been patented, and that it's just changed the way the technology roadmap played out. So Bob's idea always was that students are smart, and they'll come up with things that practicing engineers who've been doing the same thing for 30 or 40 years just won't be able to see. And I think that that's true. And I think so we're very open and very excited about what you all do. And I think that it's quite possible that something that you think of that whether, and it could be on any part of this, it could be in the Bluetooth processing, could be in the cryptographic layer, whatever it might be, will change what we end up doing. And I know that Professor Avest would feel exactly the same way. And I think that, we're just very excited about the project you all are about to do. We'll be watching very closely.
Great, thanks. Another question, what are your thoughts on the rotating key encryption from Apple and Google?
I think that what they do is very good. We have almost no issues with layer 2. The way that they do layer 2 is almost exactly what was in the PACT specification. Of course, there's always the devil's in the details. There's always things can be slightly different. As I said, I was just on a call with them. We were not arguing, but discussing down in the minutia of exactly some of those things. So we're not, but layer 2 is good. It's solid. it will be good. It's layer 1. Layer 3 is just engineering. Layer 2 is where crypto is important, but it's good. Layer 1 is where the problem is, and that is, you know, getting that too close for too long to work with Bluetooth. And if it can't work with Bluetooth, then shifting to something like ultrasound is what is where the big technical challenge is.
Okay, I think we have time for maybe 1 or 2 more questions. If there are others that are coming in, you can type them in the Q&A. I think we've talked a little bit about what happens as you cross state boundaries and centralized versus decentralized. How are the chirps randomized and made anonymous?
So it turns out that and I'll talk about it at a high level. You can read the spec at a lower level. But basically, there are random seeds that are present in each, that are created in each phone. And those seeds can be used to generate what are called pseudo-random numbers. So they're not, you know, nothing's perfectly random, but these are numbers that for cryptographic purposes are random. And there's nothing about the phone or the person using the phone that has anything to do with the generation of those numbers. And those numbers change. I've forgotten exactly how often. It was once every half hour, once every 2 hours.
I think it's every 15 minutes or
whatever
so.
it is. And those numbers, so they change frequently. But if you know the seed, you can know what that number would have been as a function of time. And so when you're listening for chirps, what you can't do, what's hard to do, is to go backwards. You can't use the chirps to figure out the seed. But if you know the seed, you can figure out the chirps. And so when you listen for the chirps that you that you heard, and then later on, what they will send you are the seeds, basically, from the sick people phones. And what you will do is take those seeds. You'll know for the last 14 days what the chirps would have been that the sick person would have sent you. And then you match that up with the chirps you actually heard. And you might think that, oh, that's a lot of chirps to remember, might take a lot of memory or a lot of compute time. But actually, these phones are so fast and have so much memory, that's actually not a problem at all.
Okay, let's see.
By the way, I should point out, I didn't mean, I'm looking here at the chat, I didn't mean to throw Google exactly under the privacy bus, but I think it's fair to say that Apple does not sell our data. Google sells our data. That's how they make money. If it's free, then we're the product. But what I will say is that on this project, Apple and Google on this project are like mom and dad. There is no daylight between Apple and Google when we ask them questions or we ask them to do something, whatever. It's not like we can go ask mom, and if she says no, we can go ask dad. They speak one voice, and it's a very intelligent, mature, a privacy-loving voice and health-loving voice, right? They want, these are, even though these two companies are fierce competitors, in this case, they are working as close together as if, at least it looks like to us, as if they were the same company. And they're doing everything right. They really are. And the only issues we have are always just trade-offs between how good we can make this work and how much battery it's going to cost and how much trouble it's going to be to change the operating system and how much testing that's going to take. So these are all reasonable engineering things. So I may have used words that made you think that I don't respect their love of privacy. It's not true. It's just Apple and Google have different business models, and that's okay. But for this project, it's the best it could possibly be, and we're so fortunate and we're grateful that they are working with us and that they're listening to. And we're not the only ones they're working with, but that they're working with us and they're listening to what we're saying. We're very grateful.
Okay, so maybe we can take one last question, and that relates to ultrasound. Do you encourage trying out ultrasound? And if ultrasound works better at proximity detection, why not use Bluetooth as a supplement?
Great question. So Jen can speak to whether using ultrasound is in scope or out of scope for the BWSI project. Maybe you want to do that first.
So I think the priority should be on the Bluetooth, but if you have ideas and you want to play around,
right. On the PACT side, the problem with the problem with ultrasound, there are two problems with ultrasound. One problem has to do with battery usage. So as you probably know, The way Bluetooth works on these phones is that Bluetooth transmissions are almost free. You can do that all the time. It uses almost no battery power. What costs battery is listening for Bluetooth. And that's why they're only listening, I think, every 5 minutes, and it's like only for a few seconds every 5 minutes. With ultrasound, both transmitting and receiving costs battery time. And so you probably would, maybe you'd use the Bluetooth to figure out when to listen for the ultrasound. And that people have been demonstrating that on the MIT campus. They've been demonstrating that, CMU has been doing that. We've been doing it at Lincoln. And what you'll find is, but if you do it, you'll find that it works great. The problem is the battery usage. But then the other problem is that, well, first of all, to get the battery usage down to an acceptable level, they'd have to make some significant changes to the operating system of both Apple and Google, which they may not be willing to do. We don't know. Some of it will never be as good as Bluetooth because Bluetooth is supported by specific integrated circuits in the low energy integrated circuits in the phones that for which there is no support for ultrasound. But then the other problem is just the perception. So ultrasound uses the microphone, and so you'd have to turn the microphone on and off. And that would probably have to be done in the operating system. And for a lot of people, hearing that Apple and Google are turning your microphone on and off doesn't make them feel warm and fuzzy, right? They're like, oh, you're going to turn the microphone on and you're going to spy on me, whatever. But the reality is that Apple and Google already turn the microphone on and off just to make your phone work, just to make it so that you can make phone calls, just to make it so that, Siri works and Hey Google and et cetera. So we're already trusting Apple and Google with the microphone as it is. So probably it's true that having them, if ultrasound really worked better and if we could solve the battery problem, then maybe we could convince ourselves, I could probably convince myself that it wasn't an additional privacy risk. But the rest of the world, when I explain this to people, they really don't understand how the Bluetooth works. They think it's GPS. They're very concerned about they just think we're tracking them. And so if you tell them, it's very hard to get them to even understand that the Bluetooth proximity is not a tracking system. And so then if you tell them you're going to be turning the microphone on, it just goes from bad to worse. And so you have an even bigger privacy perception problem, not a real privacy problem. And so I'm not sure we'll ever get there.
All right, Marc. Well, thank you very much for joining us today. This was a great talk, and I hope all of you, enjoyed it and learned a lot. And we'll keep with our seminar series. We'll start again next Monday, where we have Dr. Louise Ivers from Mass General Hospital, and she's going to talk about the public health side of PACT and contact tracing and where it fits in. Okay, so thank you all very much.
See ya.
Have a good afternoon.